say we've got a function of two variables, z equals f of xy, x squared y plus 3x squared plus 4y minus 5. That's our function of two variables whose domain is the entire plane and whose codomain is the real numbers. Technically, when I write this notation, when I write the R2 there, I don't necessarily mean the domain is the entire plane, though it often is. It might be the entire plane, take away one point, or the entire plane, take away one line, or some examples. So it could be a subset of this. But I am sort of emphasizing the elements of the domain, the points are two-dimensional points by writing R2. And then this is called the codomain. The outputs are real numbers. I'm not saying that the function is onto when I write this. It's possible that you can't get every real number as a possible output. That's a possibility. Does that happen with this function or not? We have to explore it and see whether it happens or not. But I want to find partial derivatives, rates of change in two different directions, the x direction and the y direction. Probably the hardest part about partial derivatives initially is all the various kinds of notations for partial derivatives. If, for example, I wanted to take the partial derivative of z with respect to x, I could just real shorthand use z sub x. Another shorthand is the analog of Leibniz notation, dz dx, but this is traditional within partial derivatives. You don't make your d's ordinary d's, you make them curvy d's. Are there really even d's anymore? I don't know. Some people call that del. Usually people just still say d, dz dx. It actually wouldn't be wrong to still use an ordinary d. It's just traditional to use a cursive kind of d, Adele, whatever. I don't mean the singer, Adele. Adele, okay? Del is a symbol for this. It's traditional to emphasize, to remind yourself, hey, this is a function of more than one variable. That's kind of what the idea is. You could also write this as the partial of f with respect to x to emphasize the function name. Technically, writing either and or both of those, you might say is abusive notation. There I'm using the dependent variable, there I'm using the function name, but again, we don't think of it as too big of a deal. We might as well also use the subscript there as well. Although if we use the subscript there, it's a little bit more traditional to put the fact that this is going to be a function of x and y in there. So all these are various notations for the partial derivative of this function f with respect to x. Technically speaking, by definition, it's a limit. It's a limit of a difference quotient, just like in Calc 1. I'll use the h notation as h goes to 0 of what? You want to realize that when you're differentiating with respect to x, you hold y fixed. You pretend in your mind that y is fixed. That's how you think about these things. And symbolically, that has the effect of, well, only adding h to x, but not to y in the numerator here of the difference quotient. And yes, I suppose we should do one limit calculation. I don't remember offhand if it's one of the homework problems or not, but theoretically, this is something you should be able to do on the test, maybe with a simpler example. But let's go ahead and, take a deep breath and do it anyway. Are you ready? The limit as h goes to 0 of first f of x plus h comma y. That means in this formula, everywhere I see an x, replace it with x plus h. everywhere I see a y, leave it as a y. So I get, looking right there, x plus h quantity squared times y. Oh, do we really need to do this? Okay, yeah, we are doing it once. Plus 3 times the quantity x plus h squared. At least it's a quadratic there and not a cubic. Plus 4y minus 5. All that is f of x plus h comma y. Right? In the original formula, I replaced all the x's with x plus h and left all the y's as y's. Now I have to subtract f of x, y, so that's the original formula. X squared y plus 3x squared plus 4y minus 5. Big fraction here. What you're hoping is that everything not involving an h completely cancels, so that you can then factor out an h of what's left, and then divide it out with the h in the bottom, and then plug in h equals 0, just like in Calc 1. It's just a more complicated calculation. I do get some cancellation right away. The 4y here cancels with the minus 4y there. The minus 5 here cancels with the plus 5 there. 2 minuses make a plus. Those cancel. I do have to distribute the minus sign through to the other two terms as well, but they don't seemingly, at least not immediately, cancel. They will cancel eventually. Expand this, FOIL x plus h, and also multiply by y. I'll get x squared y plus 2xhy plus h squared y. That's how this thing I'm pointing at expands. Go to the next term, x plus h quantity squared, and then times 3 gives plus 3x squared plus 6xh plus 3h squared. Distribute the minus sign through on the terms I haven't canceled yet, a minus x squared y and a minus 3x squared, all divided by h. We're hoping everything that doesn't involve an h cancels, the 3x squareds cancel. And the x squared times y's cancel. Nothing else cancels. And everything else does have at least one factor of h that can be factored out. Factoring it out of that term leaves me with a 2xy. Factoring it out of this term leaves me with a y times h, or h times y. Factoring in h out of this one leaves me with a 6x, and factoring in h out of this one leaves me with a 3h. Divide out the h's, which is okay because technically speaking, the limit is independent of what actually happens to this expression when h actually equals 0. If I graph this as a function of h, thinking of x and y as fixed, it would have a hole in its graph at h equals 0. I can evaluate the limit by plugging in h equals 0 into this one. It's a continuous function of h. Now substitute. Looks like the answer for the partial derivative of the original function with respect to x is 2xy plus 6h, or 6x. Could we have done this without limits? Sure. And that's what we mostly want to do. Again, the original formula is x squared y plus 3x squared plus 4y minus 5. To find the partial of this with respect to x, differentiate it with respect to x. Treat the y as a constant. Is it a constant? Well, it depends on how you're thinking about it. Think about it as a constant. Imagine you're holding y fixed. I mean, you could hold different y's fixed, but you're imagining y is something specific. So when you differentiate x squared times y with respect to x, you know, you can pretend the y is a 10. 10x squared differentiates to 20x. 10 times 2 times x. The constant has to stay there. I will probably do this notation mostly for my partial derivative. Differentiate that with respect to x, get 2xy, or 2yx if you prefer. Differentiate that with respect to x, get 6x. Differentiate this with respect to x. There's no x there, so it differentiates to 0, and so does that. And I got the same answer, 2xy plus 6x. Partial of f with respect to the other variable, y. zy, or partial z, partial y. dz, dy if you prefer. Partial f, partial y. df, dy if you prefer. Fy, or probably mostly I'll write it like this, Fy of xy. I differentiate this formula with respect to y, treating x as a constant. With the first one, that's a constant times y. Its derivative with respect to y is just a constant. Second one doesn't involve a y. Its derivative with respect to y is 0. Third term, its derivative with respect to y is 4. Fourth term differentiates to 0. The partial with respect to y is x squared plus 4. When we found this one, we thought of y is fixed. When we found this one, we thought of x is fixed. In general, the answers can depend still on both x and y. And at the end, once we've done the differentiation, we could then change our perspective again and say, hey, I calculated this pretending y is fixed, but now I can let y change. And I could think of this as a function of two variables. Same thing here in general, though we didn't get any y's. We could have. Computing these things is important. More important is the interpretation as rates of change. Does that mean as slopes? If you're careful, it means that. Formula is x squared times y plus 3x squared plus 4y minus 5. If I want to confirm my partial derivative calculations, the quickest way to do that here with two variables is not to use a prime, but instead to use a d, capital D. With that kind of syntax, that'll differentiate. The comma x at the end means with respect to x. And if I put a comma y, then it'll be with respect to y. If you like, you could do something like this. You could define what fx and xy are using these formulas. Just copy and paste, say. Something I've forgotten to mention in Mathematica. Do you notice that there's a space between two variables like that? It is assumed they're being multiplied. If you didn't put a space between them, if you put them next to each other like that, x, y, Mathematica would assume that's a single variable, x, y, not two separate variables that are being multiplied. As a default, it's best probably to put a star on there. Maybe you already know that. But I'm reminding you in case you don't. I'll just type in this equation here. Okay, how do you interpret these things? Can they be interpreted as slopes and or rates of change? Yes, though you have to be careful. If I plot the original function, plot 3D, there's the graph. It's hard to say whether this is the most ideal domain. You know, what we're going to be interested in after spring break with these things is optimization. Trying to find maxima, minima, and what are called saddle points, which I've already hinted at. And that means we're looking for low and high points of graphs. it doesn't look like we're hitting any lower or high points here visually, at least. Maybe my domain is not big enough to see it. Or maybe, actually, it's the case that in this case, how do you find maxes and mins in Calc 1? You set the derivative equal to 0 and solve for the critical points, solve for x. Here you set the both partial derivatives equal to 0 and solve for x and y. However, in this example, the partial with respect to y is never 0. It's always positive when x and y are real numbers. So there won't be a max or min. But we can still interpret these derivatives as slopes. For example, what's the partial derivative in the x direction at the point, say x is 2, y is 1? Plug in the numbers, you get 16. Let's try a different point where maybe we get a smaller number closer to 0. Let's try -1, 1, -8. What's the partial with respect to y at the same point? Fy -1, 1 is +5. So at the point x equals -1, y equals +1, we have just found that this has a value of -8, and this one has a value of +5. So if I was to try to interpret this with a not ideal drawing by hand, how would I attempt to do it? If I would do my typical thing of making the positive x-axis come out of the screen at you and make the positive y-axis go this way, negative x-axis going into the screen, positive z-axis going this way. Well, I also should figure out what the function value is at -1, 1. F of -1, 1 is 3. So the point on the graph when x is -1 and y is +1, meaning above that point, it's going to have a height of 3. That'll be a 3 there. Think of that point here as being behind the screen. It's got coordinates x, y, z being -1, 1, 3. It's a point on the graph of f. The rate of change in the x direction is -8. In other words, if I held y fixed at +1 and graphed the part of the surface at that value of y through this point, the tangent line there would have a slope of -8 in the x direction, which you have to imagine three-dimensionally. The positive x-axis is coming out of the screen at you. So I've drawn this in such a way that the slope is going to be negative as you're moving towards you, coming out of the screen. Does that make sense? I mean, it looks like on a two-dimensional piece of paper that I made this line have a positive slope, positive rate of change. But no, it's got a negative slope, a negative rate of change in the positive x direction, coming out of the screen towards you. In the positive y direction, the slope is +5. Positive y direction is moving to the right. Maybe something about like that is what I would get when I intersect the plane where x is -1, actually, so it's behind the screen. When the plane where x is -1 gets intersected with the surface, it's going to have a slope of +5 near that point. So it's hard to draw, hard to think about, hard to visualize. Even with technology, it's a bit hard. Could I somehow see those lines in this picture? Yeah, it's a bit tricky though. Technically, I'd actually want to use parametric plot 3D to help me. How? First treat y as the constant 1 and let x vary. So notice what I'm doing here. I'm creating a three-dimensional parametric curve here where the parameter is not t, it's x. I mean, I can change it to a t if I want to, but it represents the first coordinate. The first coordinate is what's changing. The second coordinate is staying fixed at 1. The third coordinate is varying. It's the z value as x varies, but y stays at 1. I want to let x vary near -1. I'll let it go from, say, -2 to 0. I guess I'll make it red on Mathematica since I made it red on the paper. And then I also want to do that in the y direction when x is -1 and let y vary. Like this. Y varies near +1, so I should go like from 0 to +2. Let's make that one green. This is not going to be a perfect picture. And remember, also Mathematica takes this three-dimensional coordinate system and rotates it, makes the positive x-axis go to the right, and the negative x-axis, positive y-axis go into the screen. So it is going to look a little different. You could also use parametric plot to get the axes in here. Essentially, looks like the positive x-axis goes to the right here and is in the plane at the bottom of the box. It looks like, or no, not quite the bottom, a little bit above it. Let's plot the XY plane in here too. There it is. There's the XY plane. I should make these somewhat opaque. See through. Do that. So that bluish plane is the XY plane where z is 0. This graph is the graph of the function. If I rotate it like this, that's more like what I drew. And you can see the red and green curves. They're curves, they're not tangent lines, they're curves of intersection. Kind of matching more what I drew with respect to the slopes of tangents at that point. You want to see more clearly, you can continue rotating. Positive x-axis is going to the left now. Z is decreasing as x increases. The rate of change there is negative. Turn it back this way, and now the positive y-axis is going to the right. The green graph has a positive slope. Y is increasing as z is increasing as y increases. Rate of change of z with respect to y is positive. At this point, and I could change the point, and these values would change. You can do linear approximations with these things as well, just like in Calc 1. That's not our goal today. Our goal is to think about those slopes like I just talked about. Could we think about concavity? Concave up or concave down in the x or y direction? Sure, there are second order partials with various notations. Second order partials. When I say partials, that's just shorthand for partial derivatives. There's zxx, second derivative of z with respect to x twice. Could also use an f instead of a z. Could also write it as fxx, or the most common notation I'll use is fxx of xy. What does it equal? By definition, if you think of the notation this way, this means the partial of f with respect to x, take its derivative again with respect to x. If you think about it, say this way, you're taking the partial derivative with respect to x of the partial of z with respect to x. By the way, a little side comment. This kind of notation is the origin of that kind of notation. The notation in red is the reason we use the notation in blue. You're not literally, if you're ever wondering about this, you're not literally squaring anything here. You're not multiplying this del by itself. It's not del squared, though sometimes we say that. D squared. We're not literally multiplying. Also with the dx is not being literally squared. It's the fact that we're applying the derivative operator twice, effectively. The del or the d up here gets applied twice, so you put a square above it, and the del x gets applied twice, so you put a square above that. It's not a multiplication, though. It's applying the derivative operator twice. Anyway, you look at the formula for the first order partial with respect to x, and we have to differentiate that again with respect to x. Treat the y as a constant. You get 2x plus 6, right? 2x plus 6 is what the answer here is for this example. What about the second order partial with respect to y twice? Same kind of notations. Any one of these notations is fine. I will most commonly use the subscript notation for the function with the function name. In this form, we think of it this way: differentiate with respect to y, then differentiate with respect to y again. Going from left to right in this notation, we're thinking of the same kinds of operations, but you actually think about that one from right to left, inside operator to outside operator. To do it, you look at the formula for the first order partial with respect to y, this one here, and differentiate that with respect to y again. But there's no y's. So in this example, the answer is 0. Doesn't have to be 0 in general, but in this example, it is. But hey, could we mix up the partials? There's the partial of f with respect to x. It's got a y in it. Couldn't I differentiate that with respect to y as well? Sure. I could take the derivative with respect to x and then differentiate it with respect to y. With this notation, you'd write it that way. It's getting a little funny looking, isn't it? Look at that. You could also use the function name. Go back to the function itself, write it this way or this way. This is a cause of confusion for people. When I write it this way, I'm working from left to right. I differentiate with respect to x first, then with respect to y. This means the same thing, but you think of it in the right to left kind of idea. You're differentiating with respect to y what you already differentiated with respect to x. So first you differentiate with respect, then with respect to y. You work from right to left with this notation. What's the derivative of this with respect to y? Treat the x as a constant, it's 2x, right? Look at that with me here. Not everybody's looking. The derivative of that with respect to y is 2x. So 2x. And one more. The mixed partial in the other order. Zyx, meaning differentiate with respect to y first, then x. In the Leibniz notation, you write it like that, or you'd write it with the function name. Or go back to the function name and use subscripts again. Again, once more for emphasis, this is the same as differentiate with respect to y, then x. Think of it that way. Work from left to right. Are you paying attention to what I'm saying here, these subtleties? With this notation, you work from right to left. You're thinking of it this way. Differentiate inside first with respect to y first, then whatever you get for that, differentiate with respect to x. So to find out what it equals for this example, I differentiate with respect to y first. So I have to look at this one and differentiate that with respect to x, giving me 2x. Hey, we got a match. We're happy. That seems fun. Is that a coincidence? No. You'll always get a matching of these mixed order second order partials, no matter which way you do it, as long as you're dealing with nice functions. How nice? Continuous functions that have continuous first and second partial derivatives. As long as everything's a nice continuous function, then these will equal. Can you come up with non-continuous functions where these are not equal? Yes, but we don't want to do that. We're happy to consider nice examples, not weird examples where they're not equal. How do you interpret these things? With concavity, just like in Calc 1. At least for the pure second order partials you do. With the mixed, it's trickier. With the pure second order partials, at the point we were interested in here, fxx of -1, 1. -2 plus 6 is +4, positive. So does that mean in the x direction, the graph's concave up? Yes, it does. Mixed order, second order partial in the y direction. Well, that was the constant 0. So does that mean there's no concavity in the y direction? Yes. Careful, though. In the y direction, this function is linear. It is a straight line if you cut it with planes at constant values of x, because the second order derivative with respect to y twice is always 0. But if it were not always 0, but 0 at a particular point, that doesn't mean the graph's straight. You can have a second derivative that's 0 at a point without the graph being straight there, if it's just 0 at one point. Question? Did I make a mistake? Yes, you're right. Thank you. I differentiated this with respect to x incorrectly. Treat the y as constant. So yes, it should have been 2y plus 6. Thank you for catching that. This still ends up being positive, though. +8. So in the x direction, the graph's still concave up. X direction in the original picture. I forgot. Let me re-enter it. X direction goes to the right in the original picture. That's the red graph. Yeah, it's concave up. Y direction goes into the screen. In the y direction, you can see the intersection looks like a straight line. In fact, it is. For any fixed value of x, the intersection of the plane that you would get, that value of x is going to be a straight line like you see here with this green line. Even though the overall graph is not flat, it's not a plane. It's because the second order partial with respect to y twice is always 0. How do you interpret the second order mixed partial? fxy at -1, 1 equals fyx at -1, 1. Plug in x equals -1, you get -2. It's a negative mixed second order partial. This is definitely harder to interpret. Let me copy and paste this. Let's put it inside and manipulate, where I'm going to allow myself to change x and y. But I'm using x and y as parameters. It might be better to use t's now instead of x and y. Let me go to using t's. In both spots, it doesn't matter. So t is the parameter to make the red and green curves. But what I'd like to do is I'd like to allow myself to change the x and y locations, the -1 and the +1. With the manipulating animation. Let's see, x starting at -1, but possibly changing down to -2 and going up to 0. Y starting at +1, but possibly going down to 0 and up to 2. And how can I actually put those in here in a way that's going to allow me to make those changes, change all the negative ones to X's, and change all the positive ones to Y's in the parametric plots. This should allow me to change where those lines are. Though when you do make changes, it's a bit slow in the rendering. I think I can make that. It still might be slow, but I think I can make it a little bit better, perhaps, with an option called performance goal arrow quality. So listen real carefully here. In this picture, again, the blue plane is the XY plane. This point of intersection of these two curves is above the point with X coordinate -1, Y coordinate 0. Behind the screen, so to speak. Well, okay, a minute. X is going to the right. We're to the left of the origin. The origin's right around here somewhere. X is -1, Y is +1. We're going into the screen. If I let X change, if I move this slider, increase X, what should happen is the green line, yeah, the green line's got the X in it, should move to the right. And the fact that this second order partial is negative, what does it measure if I'm letting that move to the right? The green line's slope was a slope in the Y direction. It was a partial with respect to Y. I'm letting X increase now. I'm really trying to understand this rate of change. Or if you prefer, this rate of change. At the given point, being -2. At that given point, at -1, 1. The green slope was +5. This second order partial being negative means that green slope, the derivative in the Y direction, should decrease, become smaller as X increases. At least a little bit. As X increases a little bit. These are local things. So if I move this to the right, it might be difficult to see, but that green line should get lower in slope. At least at first. It is. I think you can tell. That's flatter there than it was at first. It's steeper over here. The mixed second order partial is the same in the other direction as well. If I move the other slider, let's re-enter this. Letting Y increase, the red curve is going to change. Its slope in the X direction, Fx, was -8. If I increase Y, the second order partial here being -2 means it's going to decrease from -8 to something even more negative. It'll get steeper. It's hard to tell, but it's technically getting steeper at the point of intersection. That's what the mixed second order partial is telling you near the given point. It's all a local thing. Things can change if you move too far. It's probably not enough to remember how to interpret these just from what I've said the last 5 minutes, but it's something to work on. Got 1 minute. You can apply all this kind of stuff to functions of 3 variables. You can take partial derivatives with respect to X, Y, and Z. Can you interpret them as slopes? Only as a slope on the intersection of a 3-dimensional hypersurface with a 3-dimensional hyperplane. So it's hard to draw. Also, the mixed partials can be equal, even if you do more than 2 of them. Like if you did Fxyz, that's the same as Fyzx, for example, or Zxy, blah, etc. And some of those might be easier to compute than others. That could come up on the homework. Choosing which order to differentiate with respect to can affect how much work you do. You'll see an example in the book like that too.